Okay, so in this video, we're going to be talking about properties of exponents. We're going to be starting relatively simply, and then we're going to work our way up to a bit more complexity. Now, properties of exponents, exponents themselves are built on multiplication, somewhat in the same way that multiplication is itself built on addition. A number raised to a power, the power being the exponent, the small number as a superscript, is telling us essentially that this is the number of times that I am going to multiply the number in the base by itself. So if I multiply 2 by itself 5 times 2 times 2 times 2 times 2 times 2, that is the equivalent of 2 to the 5th power. So that's what the exponent stands for. Now, all of the properties of exponents that we're going to see are going to be derived from more or less this basic idea. So if I want to multiply two numbers with the same base by each other, but with different exponents, how would that work? So 2 cubed times 2 to the 4th. Well, 2 cubed is 2 times 2 times 2. And then 2 to the 4th is 2 times 2 times 2 times 2. So there's altogether 7 2's. So the general property is that if I have some base to the m times the same base to the n, a different number, then the result is going to be a to the m plus n. So in this case, 2 cubed times 2 to the 4th is going to be 2 to the 3 plus 4, which is 2 to the 7th. And we can see why that is the case when we spell it out. How many 2's do I actually have? I've got 3 here, I've got 4 there, add them all up, I get 7. Now, if I'm dealing with different bases to the same exponent, then I can also sort of multiply this out like this. So suppose I have 2 cubed and 5 cubed. Well, 2 cubed is 2 times 2 times 2, and 5 cubed is 5 times 5 times 5. And what I can do is I can rearrange these into groups of pairs of 2 and 5 in this example. So there's 3 of these groups of 2 times 5. And so I can multiply the bases together to get 10 cubed. Now, the important thing is that this only works when the bases are different, but the powers are the same. If the bases are different, but the powers are different, you can't do this because they won't pair up pair by pair. You won't have the same number of pairs of these different exponents. So when they have the same exponent, you can multiply the base. So a to the n times b to the n, so same exponent, you can get ab to the n. So you can multiply the bases. But again, only when the exponent is the same. If they're different, then you can't do this. That does not work because you would have to evaluate the exponents before the multiplication and not multiplication before exponents, this would violate the order of operations. The only reason this works is because there's exactly the same number of A's and the same number of B's. Now, another property that you can use is when you raise an exponent to an exponent. Now, again, if we multiply this out, then we're getting 2 times 2 times 2. And then we're doing that 4 times. So there's 2 cubed, and that's 2 cubed. And then that's a 2 cubed. And then that's a 2 cubed. So how many 2's are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 2 to the 12th. So our general property is a to the m to the n. So raising an exponent to an exponent is going to be, the new exponent will be the product of the 2 exponents, because I have 3 here and I'm using it 4 different times. So I get multiplication. So again, notice that's different than multiplying 2 bases that are the same. There we add power to a power, we multiply. Now, things start getting a little bit more interesting when we introduce negative exponent properties. So 2 to the -1, just to indicate what the negative is going to stand for in the exponent, since the standard exponent procedure represents multiplication. When you introduce a negative, you're telling the notation, I'm going to do the opposite of what I would normally do. The opposite of multiplication is division. And so the negative exponent here means not that I'm going to multiply by 2, but that I am dividing by 2. So this is again, a general rule, a to the -1. We'll jump to the n in a second. A to the -1 is the reciprocal of the base. So you divide by the base instead of multiplying by the base. When you have 2 cubed, or sorry, 2 to the -3, you can evaluate this a couple of different ways. So we can use our property of multiplication, and we can extract, this is essentially 2 cubed raised to the -1 power, or we could think of this as 2 to the -1 power and then cubed, because -1 times 3 in any order is going to be -3. Now, in the first case, that reciprocal is acting on 2 cubed. So that would be 1 over 2 cubed. So we're dividing by 2 cubed. Or in the other case, we would be saying 1/2 cubed. And either of these is equivalent to each other. They are both going to simplify to the same thing. Because this cube will apply both to the 1 and to the 2. 1 cubed is 1, 2 cubed is 2 cubed. 2 cubed is 8. And both of these expressions, you're going to get 1 over 8. So you can think of these in either way. Typically, we think of them in terms of whatever is simplest for us to evaluate. But again, this general property, a to the -n, is going to be thought of as 1 over a to the n. So now we have our negatives involved. When we include negatives, we can also include division. So what happens if we have 2 to the 7th divided by 2 to the 5th? Well, we can think of this as a couple of different ways. So one way we can think about this is multiplying this out. . That's 4. That's 6. That's 7. And then that's 3. That's 4. That's 5. So when we're doing division like this, our 2's would cancel in pairs. So that one cancels with that one. And then this one cancels with that one. And then this one is going to cancel with that one. And this one is going to cancel with that one. And this one is going to cancel with that one. And what we're left with is 2 times 2, which is 2 squared. And what that is equivalent to is 2 to the exponent on top minus the exponent on the bottom. So again, our general rule is that a to the m divided by a to the n is going to be equal to a to the m minus n. So division, again, is represented in exponent notation as subtraction in our exponents. So now that is going to work regardless of whether the exponents are positive or negative. So one thing that you can kind of keep in mind is, for instance, if I did 3 to the 7th divided by 3 to the negative 4th, well, even if I'm doing division, this is still 3 to the 7 minus a minus 4, which is equivalent to 3 to the 11th, because minus a minus gives me a plus. So 7 plus 4 would be 11. Again, another way to think about this would be 3 to the 7th. And then because the negative is in the denominator, when you do the reciprocal of that, you make it positive. So this would be equivalent. When you take it out of the denominator, you make the exponent positive. Or again, when you have a negative exponent, if you move it from the denominator to the numerator or from the numerator to the denominator, you flip the sign of the exponent and you still get the same thing. Any operation is valid as long as all of these rules give you exactly the same result. Now, the tricky part about exponents is that you can also get into rational exponents. And so the rational exponent, the sort of the base one, 4 to the 1/2 power, is equivalent to the square root of 4. And 8 to the 1/3 power is equivalent to the cube root of 8. And so broadly speaking, a to the 1/n is equal to the nth root of a. So essentially we're asking ourselves, given the index, how many times do I have to, what number do I have to multiply by this number n times in order to obtain a? So the nth root of a, the square root of a, how many times do I have to multiply a number by itself 2 times to get 4? What number do I have to multiply by itself to get 4 is 2. What number do I have to multiply by itself 3 times in order to get 8? That's also 2. When you're not dealing with perfect a to the a cubed, a to the 4th, an, etc., this can be, of course, more complicated, but your calculator will evaluate it And one of the ways that you get this nth root in your calculator is to use the fractional exponents. Now, in your calculator, of course, the thing to keep in mind is that you do have to put parentheses around your exponents when you're doing it, especially in your TI calculator. All right, so that sort of brings us to this general idea that a to the 1 over n raised to the n is going to be a, which again is the same way of saying that the nth root of a to the n, or a to the n, the nth root raised to the n power, again, the operations don't really make any difference, they cancel. However, if n is even, then technically this answer is not just a, it's the absolute value of a. Now, this can be a little bit tricky. And the reason that this happens is because when you take a negative number and you raise it to an even power, you get an even number. And then when you take the root of it, then you get the principal root is the positive root. And so if a was originally positive, then you'll get a back. But if a was originally negative, if the power is even, you'll only get the absolute value back. You won't get the original negative sign back. When n is odd, however, odd powers preserve the sign, and so you will get the sign back when you actually take the cube root of the cube. But when you take the square root of the square, or the fourth root of the fourth power, those even powers have canceled your negatives. So again, that's something to kind of keep in mind as you're working through problems. Sometimes they'll ask you to simplify problems, and this will be the exact kind of things that you will have to keep in mind. Now, dealing with negatives under even powered roots is something that we're going to deal with in another video on complex numbers. So we're not going to go into those there, but that is something to kind of keep in mind. If you're trying to take the square root of a negative number, you will get a not real solution. And so you won't necessarily get this back at all because you won't have a real number. Again, we could extend these rules to deal with complex numbers, but that's for another video. Typically, when we're dealing with exponents like this, we're only dealing with real numbers to start with. Now, we can combine all of these rules, again, with our variables, not necessarily even just real numbers. The assumption that we have a real number, but we don't know what exact number it is, to simplify more complex expressions. So combining all of our rules, we might have something like x cubed y to the fifth divided by x to the fourth y squared. And we might want to say, so how would we simplify this expression? So typically what we would do is we would apply our rules first by separating out the variables that are in common. And then we would simplify each of those. Now, when we were dealing with the negative exponents before, we were subtracting. So one thing we can do is we can say the x expression here is x to the 3 minus 4, and y is to the 5 minus 2. That's a way that we can simplify this. This would become x to the negative 1 and y to the 3. Now, often when you're doing these problems, the directions will explicitly tell you that you want all of your final exponents in your final answer to be positive. And in that case, since I have x to the -1, the way that I make this positive is I use my property that x to the -1 is 1 over x. And so I move my x into the denominator. So this will become y cubed. That has a positive exponent. It stays where it is. And then x to the 1 goes into the denominator. Now, if it's not negative, I don't write the 1. It's redundant. It's assumed to be 1 if there's no exponent there. But now I don't have x to the -1 anymore. I have 1 over x. And again, multiplying 1 by y cubed, I don't need the 1 as a placeholder. It gets absorbed. It's assumed to be a coefficient of 1 in the y cubed. So I just move the x into the denominator. Again, this is the standard way that we do simplifying. You can, of course, get much more complicated expressions. A to the -3, b b squared to the 4th divided by a to the -7, b to the 12th. You know, you could have multiple variables in addition to a's and b's. You could have a, b, c, x, y, z. But again, fundamentally, all the rules remain the same. We can separate out our a's and our b's. Oops. That didn't quite work the way I had intended it to. There we go. Now, again, our a's, we can just apply the rules. A to the -3 minus a -7. Do be careful with the signs. And then this would be b to the 8th because we're multiplying exponent raised to another exponent. -12. And so -3 plus 7 is going to be a to the 4th and b to the 4th. And in this case, we're done. Now, again, this is not necessarily the only way that you can simplify. You could, for instance, move your a to the 7th to the numerator to make it positive. And then move your a cubed to the denominator to make it positive. And then when you simplify, you're still going to end up with the exact same answer. So one thing to kind of keep in mind when you're doing these exponent simplifying problems is that you don't have to worry about like which order do I have to apply these rules in. You don't have to worry about which order you apply the rules in. You can apply the rules in any order that seems like it's going to be simpler for you to proceed. So if you first want to get rid of all of your negatives because maybe you tend to lose negative signs like I do, then that's perfectly fine. Take your negative exponent, put it in the opposite part of your fraction, and then flip the sign of your exponent. And now you have all positive numbers to work with. Actually, this should be a -4. See, I told you I lose minus signs all the time. And so when you have a -4, then you put the 4 back into the denominator. Now, in this particular case, since we have a and b the same, and the same a and b are different, but the exponent is the same, we could write this as this. But again, depending on the problem that you're dealing with, that may or may not help you simplify. If you know what a and b are and they reduce, then this will be useful for reducing. If you're just asked to simplify the exponents and combine all of your bases into a single base, then this version is probably where you want to stop. But again, what order you apply these in is not that important. Simply applying them correctly and then getting to a point where your expression is as simple as possible is the goal. So don't stress over like which rule should I apply first. It doesn't matter. Apply a rule that will get you something simpler than what you have now. And then just keep applying rules until your expression is as simple as it can be and no more rules can be applied.